Welcome back to this video lecture series on data structure and algorithms. So today we'll be discussing about two topics. The first topic is time and space complexity. So what is time complexity? The total number of steps involved in a solution to solve a problem is a function of the size of the problem, which is the measure of that problem's time complexity, while the space complexity is measured by using polynomial amounts of memory with an infinite amount of time. The difference between the time complexity and space complexity is that space can be reused, and determinism or non-determinism do not affect the space complexity. Moving on to the next topic, that is the asymptotic notations. So these are the very foundation things of any kind of algorithmic progress or approach. These are the measures by which we can analyze the efficiency of an algorithm. So there are mainly three types of notations, and starting with the big O notation. So for a given function g of n, the set of functions denoted by big O of g of n it can be defined as big O of g of n is equal to f of n, such that there exists positive constants c and k, such that big O is less than equals to f of n less than equals to c into g of n for all n having values greater than or is equals to k. The thing is, if this is the case, that big O of g of n is denoted by this set of functions, g of n is said to be asymptotic upper bound for f of n. F of n is equals to big O of g of n should be considered as f of n is at most g of n up to constant factors. We can take up an example for this big O notation. So if the question is like is 2n plus 7 is having a time complexity of a big O of n. So let's say that t of n is equals to 2n plus 7, which means we can obviously write like n into inside the bracket 2 plus 7 by n. Now if we take up a value of 7 for n, then the value of the t of n stands out as 3. So from this what we can conclude is that t of n is less than equals to 3n for all n having values greater than or equals to 7. So this is the upper bound of this. So we can surely say that t of n is equal to big O of n. Next notation is the omega notation. For a function g of n, the omega of g of n is denoted by the set of function f of n, such that there exist positive constants c and k, such that big omega is less than equals to c into g of n and less than equals to f of n for all n values having greater than or equals to k. Omega notation provides an asymptotic lower bound, just the opposite of the big O notation. G of n is an asymptotic lower bound for f of n. Omega notation can be useful when we have lower bound on time complexity of an algorithm. So there is this a very important difference between big O notation and omega notation. The big O notation is mostly associated with the worst case scenarios, and omega notations are mostly associated with best case scenarios. If we take up an example of insertion sort, we can see for the worst case scenario the running time complexity is big O of n square, and for the best case scenario the running time complexity is omega of n. The last notation that we will be talking here is the theta notation. For a given function g of n, theta of g of n can be defined or denoted by a set of function f of n such that there exists positive constants c1, c2 and k in such a way that theta less than equals to c1 into g of n less than equals to f of n less than equals to c2 into g of n for all the values of n having a value greater than or equals to k. So this above definition means if f of n is theta of g of n, then the value f of n is always between c1 into g of n and c2 into g of n for large values of n, that is n greater than or equals to k. The definition of theta also requires that f of n must be non-negative for values of n greater than k. So these were all the asymptotic notations that we use in order to analyze the efficiency and potential of any algorithmic approach we will encounter. Thank you for watching this video and staying with us. See you next time.